Okay, so we've seen the story of the electron, and understanding the proton was also being discovered at the same time because those two had to be partnered. The next particle we want to talk about is the structure of the nucleus itself and the discovery of the last particle we didn't know about, which is the neutron. So that had to come from radiation. Materials that were so big they were falling apart and giving off radiation in the process, things like uranium or radium or other heavy elements. So Roentgen is the first to discover this idea that something's coming out of an atom and it can pierce through your bones or your skin. As a matter of fact, when he held it in his hand and he put his hand over a piece of film, he later developed it and was freaking out a little bit that he thought it was sort of mystical. And as a matter of fact, when he showed his wife, she was a little freaked out that it wasn't something, spiritual in nature, like an evil or some force. But they came down to understand it was a regular phenomena that this material has giving off some sort of radiation that's developing the film underneath. It didn't take many years, even one more year, in that Henry Becquerel was able to figure out what that substance was. It was uranium inside of this ore. Roentgen was just using certain metal ore and he was holding it, but Becquerel was able to isolate it down to uranium, which encouraged Pierre and Madame Mary and Pierre Curie, to go and try to find those and isolate it. And you'll notice it took them maybe a few years. It was done in a terribly small shack outside behind the university, and they were able to isolate uranium and radium. Within a dozen years, they were able to find polonium as well. For that, both of them received Nobel Prizes. But it was that material, to be able to isolate it, that others around the world wanted to study. As a matter of fact, Rutherford had dozens and dozens of graduate students that went on to all get Nobel Prizes and that were great in physics. So he really was sort of the grandfather of all of these pioneers that were out there. Decided to put some of the radioactive material in what looked like a cannon. And then any particles that escape would at least be directionally pointed out the end of that cannon. And he decided, well, let's see what we can do. It's like a kid who got some big old object and says, well, let's see what happens when it runs into this, into a big old mess. It's the scientific equivalent, we'll say. And so he was shooting these particles at gold, and gold was the most dense material that he could find. I suppose lead would have been another example, but gold is a little more dense. So he thought that'd be our great target. Trouble is he didn't have an understanding of where the nucleus was or where the matter was. Now, if it was all smeared out nice and big, it would be like shooting these particles coming off are just small particles. We didn't know that quite yet either, but they should hit that and stop. I mean, it's like wearing lead vest when you're doing x-rays. It should stop them. What he was surprised to see is most of them, 80, 95% of them, went straight through. Didn't hit anything. But only once in a while would one come off at this huge angle. He thought these particles coming off were high energy things because they saw them pass right through bone. And so to him, it was like shooting a cannon at a piece of tissue paper and having it bounce off. What he didn't realize is that the nucleus, because it has gold, for instance, has 200 particles in the nucleus. This particle that's coming off as a decay only has 4 particles. It's a helium nucleus, basically, 2 protons, 2 neutrons. So we've already seen in those fail videos of a kid running with an exercise ball and he hits some big grown-up that the kid goes flying backwards because he's so much smaller mass. And that's what the same thing he concluded, that the mass must be completely very concentrated. As a matter of fact, he made an estimate based on how many came straight through. And that's where we're getting to understand that size, that all of the mass is in 1/100,000th of the space in the middle of the nucleus. So very few, 1% maybe, gets reflected out in these huge high angles. Rutherford also characterized all the particles coming off of that radioactive material as helium particles, the nucleus of 2 protons, 2 neutrons. Some are smaller, they're just electrons because they'll hit something and they could measure it based on the electricity that flowed. Or it's just given off as light, gamma radiation, very high power light. And so that was the start of understanding about radiation for them as well. As a matter of fact, he showed as he took that helium and smashed it into some subjects, he was the first to really transmute, change one atom into another. You're going to notice, remember, these are the protons. Here's the number of protons, neutrons, and the number of protons. That he added 1 proton and 1 gets kicked out after they interact, and hydrogen comes off on its own, but 1 stays behind to change that substance. So here's where that number system becomes useful when you're looking at nuclear reactions that we learned about in that previous case. It was though Chadwick that came up to understand the neutron. Chadwick is actually saying, I'm not going to use something that's electric field or anything like that. So I'm going to use a felt piece of cloth with alcohol on it, and I'll put it on dry ice. What that does is supersaturates the air so that any little particle, even an electron or a proton or something that goes through there, will leave a vapor trail like a jet high in the atmosphere. And so what he does is he notices, here's this proton because it's curling in one direction. This must be an electron because it's curling in the opposite direction because they're in a magnetic field in this thing. But he notices that there are some things that come off and are going straight. He said that must be a particle that has no charge. And so he was able to postulate and show evidence of the neutron in that example of a cloud chamber. What ended up becoming the application of those is because neutrons have no charge, it's easy to get them to be introduced into a nucleus. If you try to push a proton into a nucleus, that positive charge is going to feel all those positive charges. There's no way. It'd be hard to hit. It would never get close enough to do this. But a neutron will go in unaffected, and what it does, it makes the atom oblong or too big, and it gets to be just the right size that the internal positives hate each other enough that they'll rip apart. And that we call fission. Fission is splitting of the atom. What's interesting, though, is when that atom splits, a couple extra protons are given out. And if there's enough mass around there that those neutrons get sucked up into those, they'll break apart, give across 3 neutrons, more neutrons, and this will become uncontrolled, which is what we make in the atomic bomb. Now, that's the typical uranium reaction to break apart into smaller units. It doesn't have to be equal numbers. It could be barium and krypton. They actually break into 2 elements that are right around 140 and right around 90. But they can break apart in different fragments that don't always get to be barium and krypton. What's interesting is that if it left unimpeded, we noticed that a pound of uranium, or about half of a kilogram, almost consumed 2 grams. In other words, the materials after it had reacted were 2 grams lighter. From Einstein's equation that energy is the mass times the speed of light squared, which is a huge number, that's about 2 billion joules of energy. We talked about energy. That's 25 million times more than an equal amount of coal can produce. And that's why we're using it today for electric generation, is that you can get these, instead of being uncontrolled and becoming explosions, is that you can push rods down in here and then suck up the extra neutrons that are coming off. We said those extra neutrons are coming out of the reaction. If you put a carbon, like a graphite rods down there, they'll suck up those extra neutrons so they don't go hit another atom to cause that to decompose, and that helps to regulate the speed of that reaction. What happens is that then that gets to be super hot, heats up water, which goes into another coil, which heats up a second stream of water and then comes back here. That cools this water off and comes back to be reheated. And this second loop is the place where this turns into steam and turns the generator. Okay, this is still not a loop that is exposed to the environment. In case this melts down and we get nuclear material in here, it's still contained. Okay, and that's what happened to 3 Mile Island. What ends up happening is they take a local water source like a river or pump, and then they cool down that steam here so that it can be regenerated into more steam. What happened over in Russia for the meltdown of Chernobyl is that this melted down and caused the radioactive material to go into here, and then this melted down as well, and it just all blew out into the environment. But that was something we had to be super careful of. That was the discovery of the nucleus and the neutron, which helped us to make the atomic bomb and to nuclear energy.